Okay, so our next speaker will be Rachit Nigam from Cornell University. And Rachit is on the job market, so pay attention. Rachit will be talking about how to modularize hardware design with timeline types.
Well, I'll start after this actually shows my slides. Oh. Okay. Okay, perfect. It shows up there. Okay, there's a lag. Well, we've dealt with the hardest problem in CS already, AV problems. So now we can move on to hardware design. Thanks for the introduction, Fred. As you mentioned, I'm Rachit Nigam. This work was all done with my colleague, Pedro Amorim, and my advisor, Adrian Sampson. We're all at Cornell University, and we're working in the Capra group. So for a long time, we've relied on the amazingness of Moore's law to write our beautiful abstracted code and sort of have it automatically improve in its performance. But for a long time, this trend has changed. We've started building specialized hardware accelerators that can do one task and do it really, really well to get improvements in our performance. For example, if you look at something like the Apple M1 chip, we have a lot of traditional processors in the design still, but a vast majority of the area of the chip is actually dedicated to specialized accelerators like the GPUs, neural engine, and specialized accelerators for audio and video encoding. So this talk is about how we can all start building our own hardware. As we move into this future wonderland of hardware accelerators, we all must be building our own accelerators. And so let's look at some of the tools and frustrations you'll have as you try to build your own hardware. Next, I'll show you how we can use the power of type systems, a beloved tool of the PLDI community, to sort of bring some of these tools into control and build efficient designs. And I'll also show you how this type system can not only help you build efficient hardware, it can also help you integrate hardware from your favorite DSLs that can generate hardware designs. The last two things are our specific contribution in this work. So let's talk about traditional hardware design tools. On the left, you'll see sort of a pseudocode implementation of an arithmetic unit that takes an op input, and based on that, either performs an addition or a multiplication. On the right, we're going to work with the sort of minimized hardware description language like Verilog. So we work with sort of these modules that take a bunch of inputs and outputs. So we have our inputs op, L, and R, and the output out. Next, in hardware, we must structurally instantiate circuits that can perform the computations we care about. So here we want to perform additions and multiplication. So we need to instantiate circuits, adders, and multiplier to do that, and pass them the inputs. And because we're working in hardware, these signals always have sort of values on them. So we're always going to be computing the multiply and the add. And then we'll use something like a multiplexer, which is a structural instantiation of the control flow of our hardware design, to select between the output of the adder or the multiplier using the op input. So if you take this design and you try to run it, you'll see something like this. We're trying to do a multiplication between 10 and 20. And last I checked, that's not that number. So OK, we dig in. We ask our hardware friends what's wrong. And they'll tell us, you have to go and look at the waveform, right? And the waveform checkpoints the entire state of the design at every clock cycle. And we'll realize at some point that there's some weird number flowing through our design. And I'm sorry if it's hard to read, but welcome to my life. This is what I do every day, all day. I look at these waveforms and look at some numbers. I'm like, that number looks kind of suspicious, right? And so the challenge with hardware design is that all of these languages that we're working with, they're not capturing something fundamental about our sort of base primitives. So in this case, our adder is a combinational circuit, which means as soon as we provide it inputs, it will compute its output. Whereas the multiplier is a multi-cycle sequential circuit, which means it takes several cycles to perform its computation. But if we look at the signatures of our module, this is not evident, right? There's a lie by omission here. We look at the add and the multiplier, and they have the same signatures. In sort of a standard software engineering language, we can say that we can replace the adder and the multiplier. We can sort of substitute them together, but that's not really true. There's a fundamental difference between these two things. And an outcome of this is that users must program against the implementations of circuits. They must know that, hey, the multiplier takes 3 cycles. I'm going to hard code this fact in all of the places I use the multiplier. And if that changes somewhere, all my designs break. And this also sadly breaks modular reasoning. And so the fundamental problem with traditional hardware design tools is that they don't capture timing and structural constraints of the programs that we're working with. So this talk is about Filament, a new programming language that can capture temporal and structural constraints of hardware designs. The first idea in Filament is that we parameterize all our designs using a set of events which are tied to the clock. Right? Next, using these events, we can specify the availability intervals for signals. We can say that the input L is required in the first cycle, which is represented by the interval g to g+1, and then the output is guaranteed to be available only for the first cycle, which again is g to g+1. These intervals are half closed on the right-hand side, so you should read it as just g to sort of g and then g+1 half closed. Next, we can see that these interfaces are already capturing temporal properties in our hardware designs. We know that an adder is combinational, or it takes no amount of time, or it doesn't take any cycles to perform its computation because the output is available in the same cycle as the input, whereas a multiplier is sequential because it takes several cycles. Next, we can go back and start implementing our arithmetic unit. We can give our signature for our signals. We'll say we'll take all of them in the first cycle. And then we use the new keyword to instantiate circuitry in Filament. This is nothing special. This is exactly the same that we saw in a traditional hardware design language. But note here, we're not passing in the signals. That is done in Filament's novel construct called an invocation. This does not exist in standard traditional hardware design languages. What invocations do is that they schedule a computation on a circuit using a set of inputs at a particular time. And it does this by saying, when you observe the event t, you must perform the computation with the adder with the inputs L and R. This allows us to sort of explicitly express design reuse. We can say that the adder is used twice here, once at time t and another time at t+10 with different inputs. And we can go back and sort of look at this scheduling primitive, and I'll mention this here, that the language of scheduling expressions is restricted. It only allows you to write things like some event plus some natural number. And this is because Filament is a language for describing statically scheduled hardware. It's hardware whose timing behavior is independent of its inputs. Next, we can go back and fill in our design. I'll point out that instead of reading the outputs of the instances, we read the outputs of the invocations. All of this finagling gives us something useful, though. Instead of looking at that terrible waveform, you get this nice error message from Filament that says, hey, there's something wrong with your design. You're trying to use this output from the multiplier in this interval, but your multiplexer expects this input in this other cycle. And so that's what is causing a problem in our hardware design. Hardware people would call this a imbalanced pipeline. And so Filament has statically, at compile time, caught this error. To fix this, we have to instantiate something called a register, which can hold on to a signal for a couple of cycles. And because it has to hold on to a signal, we have to tell it when we're going to give it a signal and what is the last point in time when we're going to stop reading that signal. So here we're instantiating the register R, and we're saying we're going to provide the input at t, we'll stop reading it at t+4. So the well-formness property that Filament is enforcing here is that well-typed programs only read semantically valid signals. And this allows us to reject any programs that have imbalanced pipelines. With this, we can build hardware designs that are modular. If the timing behavior of your design changes, Filament will give you an error message. But they're not quite efficient yet. And they're not efficient for a very specific reason, which is that the hardware module we built is purely sequential. It processes each pair of inputs all at once and then processes the next set. In contrast, hardware designers often want to pipeline the execution of their modules and process multiple computations with the same physical resources. The property that you have to care about and worry about when you're working with these kinds of pipeline modules is initiation interval. It's the number of cycles you have to wait before your module can accept new inputs. And this is a structural constraint. Every circuit has an initiation interval, and it cannot be changed without fiddling with the implementation of the circuit itself. In Filament, we can capture this constraint and also check that it is correct. So here we're going to take our original mul module, and we're going to add a delay. For each event, we add a particular expression called the delay that completely summarizes how often the module can accept new inputs. Here we're saying the module can accept new inputs every 2 cycles. And then Filament will go in, and its type checker will ensure that this event delay 2 is sufficient to avoid all resource conflicts. And this allows us to do compositional type checking. The way Filament does this at a very high level is it has to enforce this property we call safe pipelining. It has to check for inter-iteration conflicts, which are resource conflicts that can occur while you're processing one set of inputs. So if you execute the same adder at the same time twice, that's a resource conflict, and we're not going to allow you to do that. The second set of properties we enforce are inter-iteration conflicts, which occur when you have multiple pairs of inputs being processed by the same physical resource. Together, Filament will sort of reason about this and ensure that there are no structural hazards in your design by eliminating all resource conflicts at compile time. These properties together mean that Filament can rule out a large class of structural pipelining bugs at compile time. And the outcome of this, the reason you should care about this, is that you can build APIs and reusable packages where you publish some module, and if in the future you change its timing behavior or its pipelining behavior, your users will know that something has changed and they need to change their design. Right? Again, for software people, this seems very trivial, but again, this doesn't exist in hardware. We have to sort of very carefully reason about our timing behavior. So what Filament is giving you is that kind of reasoning at the type level. Filament has a bunch of other things that I'm not going to get to talk about, like a compiler that lowers it to Verilog, and a formalism, apart from pointing out the fact that the formalism in Filament, called timeline types, is inspired by separation logic. But instead of reasoning about physical separation, it reasons about temporal separation of resource use. And you can ask me more about that. The last part of this talk, I want to show how we evaluated Filament. We want to evaluate how expressive Filament is, how many designs can it actually capture because it has this statically scheduled restriction, and how efficient are those designs. So for the expressivity evaluation, we took a bunch of open source hardware generators, some of which were published at PLDI previously, and had them all generate Verilog. Then we went in and gave type signatures for all of the Verilog modules that we generated. And we showed that Filament can capture interfaces for a variety of designs generated from DSLs. In our evaluation, we also found some bugs, but those details are in the paper. For the efficiency evaluation, we took the conf2d kernel implemented in one of our DSLs called Etherling. This is prior work, which had this benchmark already. And we compared it to a handwritten version written in Filament. And our evaluation, we sort of collected resource usage and the maximum frequency. And the underlined colored parts are the ones that show which design did better on what resource. Here it's useful to note that Etherlink uses fewer logical resources, but we use fewer registers and DSPs, which are sort of computational units, and we run at a higher frequency. This is not surprising because Etherlink is a high-level DSL to Verilog compiler, whereas with Filament, we're writing the Verilog code, and we have a lot of control on our design, which gives us a lot more ability to optimize our design. Next, we wanted to show that Filament can combine the superpowers of each DSL. So we took this other DSL called Reticle, which has the power to generate really efficient implementations of dot products. And we sort of took our Filament design and made it use the Reticle-generated dot product. And in this case, we can see that Reticle plus Filament together use dramatically fewer logical resources as well. And so this is the power of Filament. Not only can your designs be efficient if you write them in, sort of directly in Filament, you can take your favorite DSLs that can do much more sort of low-level things, give them type-safe wrappers, and call them from Filament. And you can compose them all together. So I want to wrap up this talk by saying something about modularity and efficiency and this tension that exists in hardware design languages. As PL people, we have explored a lot of DSLs that can give us modularity through compiler-based composition mechanisms. We write our designs at higher-level programming abstractions, and we can sort of compile them, and we can guarantee that they're composed in particular ways. On the other side, the hardware design community has worked a lot on building really efficient, low-level tools that can sort of give you low-level control. They don't have that much modularity, but the thing that they end up caring about a lot more often is the efficiency. Filament provides a different trade-off here. You use a type system to enforce the modularity, and once the type checking is done, you can erase the types and get Verilog that is close to handwritten Verilog. If this rings a bell, it's sort of very inspired by this pioneering work in the Rust community on fearless concurrency, where you sort of write low-level code, and you have to fight with this type checker. But once you can prove to the type checker that you have done the right thing, you get really fast designs that are also compositional. So in the spirit of acknowledging Rust, we want to use the tagline, Filament being a language for fearless hardware design. And so that was my talk on Filament. If you're curious about the work, I encourage you to go read the paper and check out our website, filamenthdl.com. As Fred mentioned, I'm on the academic and industrial research job market, so if any of this stuff sounds cool, please find me after the talk. I'll be here all day. Thank you.
I had a question about the portion where you're storing variables in a temporary register. It seems like that's potentially open to user error if they, keep the value around for too long. And it seems like if you scope it and give like some sort of thing that they want to optimize against, like pipeline length, you might be able to elide that. Is that something that you've thought of, just kind of making it less overhead for the user to think about when writing the program?
Yeah, so I think there are a couple of questions, but the important one is, can users elide this like extra information you have to add when you're using registers? And so the current system I showed you, I think it's very easy to do something like type inference if you have all the types and the signatures. That's something we have not done, but we expect that it would be easy for the language that I showed in this presentation. Filament has evolved since the publication of this paper. We have parametric designs now, and so now it's more challenging to support that inference mechanism, but we're working on that. Does that answer your question?
Yeah, thank you.
Thanks.
Hi, great talk. Tim, Princeton. I was wondering about, you mentioned that you allowed for an expression of how long something would take in terms of a variable and then a constant. Are there ever situations where you might want, say, addition of two variables to capture like a relation between multiple components?
Yeah, that's a really good question. So just to repeat the question, the language of scheduling expression is quite restricted, and so can we allow things like adding to events? Actually, adding to events doesn't quite make sense because events are these sort of, you should think of them as points on like a timeline, right? So adding two of them together doesn't lead to another point on the timeline. The older version of Filament actually had a max operation that would max between two events, but that led to dynamic scheduling, and so that created a lot of complications in trying to enforce the safe pipelining property. In sort of future directions that we're exploring, we want Filament to have dynamically scheduled circuits, so we're trying to add that back in and building this theory. I think this model of these two properties, safe pipelining and sort of well-formedness, which was the first property, give you a good litmus test to understand whether you have built a compositional hardware design language, which uses a type system. If you can enforce those two properties, you win. If you can't, then it's something weaker than Filament. I hope that answered your question.
Yeah, thank you.
Hi there, Scott Davidson, University of Washington. Really interesting stuff. I was wondering if you've given any consideration to multiple clock domains, like clock domain crossing or source synchronous communication?
Yeah, I love this question. So the question is, have we thought about sort of clock domains? So in this language, currently no, but I think there's a very clean way to add clock domains, which is that each event is tied to sort of a particular clock domain, right? So you have some notation. I'm biased to Rust, so I'll just use the lifetime notation, and I'll say G is bound to some domain C1, some other event is C2. And so normally, if you have different events in different domains, you can't interact. I think the cool part begins when you say that this clock domain is running at twice the frequency of that other one. And so then you can start saying that if I hold this signal for 2 cycles, I have synchronized with this other domain and I can pass the value in. So again, that's some work that I'm thinking about on doing, but yeah, clock domains are cool and we should have them.
Very cool, thank you.
Thanks.
This is a similar question, but I saw your example with the adder and the multiplier. I thought, oh, when you do an addition, you're going to be doing the multiplication anyway, and that could use quite a lot of power, which you could avoid by using clock gating on the multiplier. So what about clock gating? Can that be added to Filament in a nice way, do you think?
Oh, that's an interesting question. Just to repeat it, can we support things like clock gating, where we sort of turn off an event stream to a particular circuit? I think that's cool, and it requires some careful thinking because you want to use a signal to turn off the event stream that is going to the multiplier in our language of events. Yeah, I think to do that safely, I think to do it safely, it's not too hard, but it's not clear to me what the safe pipelining property means when you start clock gating. Maybe it's just trivial as you say, if this signal is asserted, turn this event stream off, and then downstream uses of that event. You can give this new clock gated event a new name, and it can only be used in domains where that condition was true. But this is a curious idea, so I'll catch you after the talk, and we can discuss this more. Thank you so much.